right. So, who can? We're gonna wait for him because this is 1, 2, 3. Have you changed your view of the world, of the digital world? A bit, at least? Yeah? Who sent me the... Okay, good. Today I don't need to finish the question. Thank you. So she sent on the WhatsApp group an image of RAM, randomly allocated memory, RAM, of 1 byte. So to make 1 megabyte, you need 1 million of those. And yeah, it was, what was the size? Like 1.5 meters of technological components. And can you guys add the new students to the WhatsApp group? You do it now. Okay. Thank you. Are you doing it? Yeah. Sophia? Ha! My memory, I'm so good. Are you in the group? Yes. Okay, this is magnesium. It's not powder of any other kind, okay? It's because I got sick. I was on the roof 2 days ago. It was raining. I'm doing the renovation of the house. I don't go to the roof. Just random. Installing the roof. So who can tell me what a transistor is? First I just want one word as definition. If you had to pick one word, what's a transistor? A switch. Very good. Now let's expand the concept. How is it such a special switch? Hmm? Okay, so why? Why did we have to wait for the transistor? What's special about the transistor that a normal switch doesn't have? You know it, come on. Okay, it can let electricity through or not, and it can increase the power of a signal. Very good. So it's not just on off. It can take any signal and amplify it. What else? How big is a transistor? 2 nanometers. So one nice thing about transistors is that they can be small. A mechanical switch, like that one, cannot be 2 nanometers big. So the revolution comes because the transistor is a switch that has no moving parts, and it can be very small. That's why we saw those gigantic mechanical computers. Those are now obsolete. We don't build like that anymore. Why? Because we can fit how many transistors in the iPhone, for example? 14 billion, 15 billion? Yeah, 15 billion transistors in the processor of the Apple. Okay. What else did we see? What can we build with a few transistors? Okay, two diodes make one transistor. If we take two diodes, we can make one transistor. What's a diode? Since you brought it up. That's the transistor. The transistor has 3 layers. The diode has 2. It can yes, it has N-type and P-type silicon semiconductor, and it forces the electricity to go in one direction only. If you combine two facing each other, you have the transistor. Okay, now I want to start again the video of last time. You remember the logic gates, right? Yeah? Okay. So you come to the board and you explain to them the whole story. To connect, yes. Let me connect first to the board. Yes. There's like a box we put it and basically there were like 2 transistors, 2 contacts. Oh, okay, wait. 2 contacts here and 1. And it's made of your head. So which is okay, so the AND logic gate means that if this one and this one are on, yes, then the output will be on. Perfect. It's a very simple concept for the AND logic gate. They called it AND because they're smart people, they're engineers, and they gave it a very simple name. AND. This and this are on. The result is that this is on. Here you can see an example. There is the source of electricity. If this switch is closed and this switch is closed, the LED will turn on. Very, very simple. The smallest logic gate you can think of. This and this are closed. Closed means it goes through. They're closed, so this turns on. Voila. Let's see another logic gate. To or. So there was a still sort of like a box. Yeah, box is fine. Then to input, and then one output. Yes. And if this one is on and this one is off, the output will be on. If both are on, it won't be on. It is that XOR, exclusive OR is only one. Okay. This can be both. Okay. So if one or both are on, then the output will be on. Exactly. All right, let's play the video. And you have video. So this is like a resume. Yeah, it's called truth table.
So in this case, it was like the zero, like
Off.
Okay. So if A, which is one of our inputs, and B, that's the other input, is off, then the output will be off. If A is off and B is on, one is on, then the output will be off. If A is on and B is off, the output will be off. A and B on, the output will be on. So
another very simple concept. Okay? There is nothing complicated behind it. What you see is exactly what we are trying to explain. Both on, the result is on. It must be this and this to have on as out. No, I should say that's another very simple logic gate, the not. If the input is 1, the output is 0. If the input is 0, the output is 1. And this is another piece of logic. Okay? Imagine when you have an entire code of a program, those are thousands of logic concepts. When you add numbers, when you subtract, those are all logic concepts. And these are the building blocks. It starts very easy, just like this. And not, that's one. This you must have bigger. So basically, which is the same thing you explained, but do it again. So there are two inputs, and linked it with the AND logic gate, and then we have one output. So what the AND logic gate does is just if one input and the other is on, then the output will be on. If one of them is not on, then the output will be off. Perfect. Let's continue. No, I mean, play the video.
Oh.
Okay. So you use twice not and one and right? Or none, none, not. And he put those components all together and he made you called or. Or. And now he's gonna use or to show that it's really or. Using here. Two digits, 0, 1, which is also on and off, or low voltage, 0 volts, high voltage, 2 volts, 5 volts, depending on what you're paying. One, 10, 11, 10, 11. So he's going to use those logic gates to create more components, logic components. Because his objective is to be able to add two numbers, like in a calculator, a digital calculator. Simply add two numbers. Very, very simple mission. He only has on-off switches available, nothing else. Remember, we used the on-off switches to make the AND, then we made the NAND, then we made the OR, but it's all switches, meaning transistors. Nothing else is available, only on-off. The important concept, 1 plus 1 equals 10. The next number after 1 is 10. The next number after 10 is 11. After 11, 100. There's nothing between 11 and 100. Okay. Report and this elementary school stuff. You just added two numbers and we only have two digits. In fact, it's easier than elementary school because 1 plus 0 is 1, 1 plus 1 is 0, carry the 1. That's it. It's really the only rules you need to know. 1 plus 1, 0, carry the 1. Yeah. So we saw it on paper, the way a human would need to do it. Now he has to transform it into digital. And this step is in between. It's one step towards the digitalization of that concept. And we saw the two numbers we are adding. There will be a result and a carry. Il report. All clear? 1 plus 1 is 0, carry the 1. So for the carry, they notice that it's just like the AND logic gate. 0 and 0 gives 0, 0 and 1 gives 0, 1 and 0 gives 0. 1 and 1 gives 1. So this is solved. The AND gate will give me the carry bit. Okay. From this point forward, take it as narrative. You don't have to learn it by heart. Just observe how magically we go from switches to a calculus. You can still understand it, but you don't need to become an expert of it. Just witness the magic. So pay attention to the magic. So he was able to replicate the truth table we saw before. From the input, he is able to have the outputs that he wants. Using, again, only switches. There is no cheating involved. You saw it. It is the XOR based on the OR, based on the NAND, based on the AND. Okay? The previous system that you saw, the one we just saw, he called it adder because it was a working adder for 2 bits. Good. Okay. So 15 plus 1 will overflow because we can write 16 with 4. And from here we go on. You will use some tricks to make negative numbers. And for multiplication, how do you think multiplication works? If I want to do 3 times 4, how would you approach this? Well, you're going to do 3 plus 3 plus 3 plus 3. You're going to do the addition 3 times. 3 plus 3 plus 3 plus 3. And other tricks to do division, to calculate an area, to take a vector and scale it, to calculate the square root of something, any vector calculation, any calculation that a graphics card may need, or calculations that are needed for an artificial intelligence or whatever you need to do. So, when you see, let's go to the internet. Okay. Transistor inside processor. Here we go. This is the dye, like the negative of the picture. And they use it with light and laser. They use it to print one chip. Chip means a group of transistors with a function. Okay. Okay. Remember the video we started for? We were connecting the logic gates together. Somewhere here, there are 20 transistors connected in a way that they can add two numbers. Of course, since we have 15 billion of them available, we can do multiple threads. The processor can do many things at the same time, so we can put more adders. Or in multiplication, you have to add many times. If we put 100 adders, when you multiply by 100, it's just one step, because you have 100 adders. And everything else, the same concept. The square root of something, the vector calculation of something, the shading on a surface in your video game, somewhere in the NVIDIA processor or whatever graphics card, somewhere in there, there are specific groups of transistors specific for 3D graphics. The shadow, the fog, the smoke, the water behavior, all those things become simple to calculate if you build his own system of transistors. Before we move on to the rest of the course, I want to go to the speed of light, the thing we saw last time, and also the size of the transistor. Current technology is 2 nanometers, meaning that the size of the transistor, or the size, the smallest thing, the smallest feature they can do is 2 nanometers. Like when you have a printer, 360 dpi, that's the detail. So this is the detail they can, the smallest detail they can make on the chip. And how many atoms of silicon is 2 nanometers? Anyone remembers? 10. Yeah. Because one silicon atom is 0.2 nanometers, and this is 10 atoms. And what's the conclusion? What do I want you to understand? That now our limit for increasing the number of transistors, our limit for making processors that have more power, more components, our limit is the size of atoms are too big for us to make smaller transistors. We reached the limit of physics, the limit of the universe, when we talk about the size of the transistor. Maybe they can get it down to 1 nanometer somehow. They can use 2 atoms, but see, that's the problem. The size of the atom. Right now, we're facing the problem that atoms are too big. Then the other problem. Anyone remembers what the other problem is? Yes, light is too slow. What's the speed of light? By heart, come on. 300,000 kilometers per second. That's from here to the moon in 1 second. Or to the moon and back in less than 2 seconds. Or, since the Earth has a circumference of 30,000 kilometers, it's around the Earth in 0.1 second. So, something like, no, that was too slow. That's the time it took for light to go around the planet once. So, how much does it take to travel only this much? To travel 1 meter, to travel 1 meter takes 1 divided by this. 1/300 millionth of a second. Un 300 milionesimo di secondo serve a fare un metro. And our processors have a frequency of, we will take this number. For simplicity, we will assume that processors have 3 gigahertz. In reality, they are 6, 4, 3.1. But on average, this is the frequency of the processor. 3 gigahertz. So every second, there are 3 billion events. So 3 miliardi di eventi al secondo. So 10 times more than this number. Questo numero è 3 miliardi di secondi. Which means that if we have 3 billion events per second, during that time, the light has traveled 10 centimeters. 1/10 of 1 meter. Se io avessi 300 milioni di eventi al secondo, 300 milioni di eventi al secondo, la luce avrebbe percorso un metro. Perché dopo 300 milioni di eventi ha percorso, cioè sì, è passato un secondo e ha fatto. Ok? Con 3 miliardi, quindi 3 billion gigahertz, events per second, the light can only travel 10. So, if my processor is in the middle of the motherboard, this is a motherboard, let's say the processor is here, and the RAM is here. This is 10 centimeters, this part. So the processor cannot send another piece of information because this one, this electron, has to travel 10 centimeters. So the processor is waiting for the light to travel 10 centimeters before the next instruction. Il processore sta letteralmente aspettando che questo elettrone, questo segnale, faccia 10 centimetri di strada alla velocità della luce. So, in digital computing, we now have these two limits. Light is too slow, atoms are too big. How are they going to solve it? Well, more processors, parallel processing, for example. So you split the job. The calculations are divided into more processors. That's why you have 16-core processor, 56-core processors. They're out there. That's the number of cores there. Everything clear? Okay, good. Now, those that missed the other classes, please go watch some videos of ancient computers. A relay computer, a valve computer, you know, old stuff. So that you see the entire history. But this is what's important now. And from now on, I believe that when you look at a computer, you truly understand what's going on. There are 15 billion transistors. What are they doing? We saw it. Nanometers, the multi-base, USA, Huawei, Taiwan, TMSC. That's the issue. How many atoms we need to make a detail, a chip, a transistor, for example. The gigahertz, the speed, the frequency of the processors. Why don't we have a 50 gigahertz PC? Well, the problem is the speed of light. 2 gigahertz was there already 20 years. It's nothing new. And now they are at 3 gigahertz. It's not moving forward. It's not like memory. It was 1 megabyte, now is 1 terabyte, 1 petabyte. Millions of times. Okay. We're stuck at 3 gigahertz because of the speed of light. Okay. Let's go to the slides. So the slides, we use these so that suppose you transfer to Rome or Dubai, another branch of SSM. Well, we are keeping a standard. I would have loved to make different slides, but these are fine. We can work very good with these as well. But how long have we been without? No, just now. Yeah. is a computer? We know. A bunch of transistors that create magic through logic. How does it work? Right? What would be its evolution? Well, definitely not smaller. Atoms are too big. Not faster. Light is too slow. It would be more processors, for example, or completely different concept like the quantum. Instead of bits, they use qubits, quantum bits. So another word, they switched completely to something. What is a program? See, but it's very simple. What is a network of computers? Now, has anyone ever written any code programs? No? 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 Ok. Preparare le pagine CSS. Esatto. Sapere i messaggi. No, C più. Sì, so, for your sake, you can go on the internet and pick any of those coding online courses, not because you want to learn coding, but because you live in this century and it's fascinating. You're just like taking a trip to Florence, you take a trip into coding. Do it. Otherwise, you're wasting your life. And the language C is like the Bible. Many books came after the Bible. C is the Bible. And C++ is a better Bible. They just improved the. Okay, in 1642, Pascal was led to develop a calculator by the numbers of mathematical calculations plus, minus, multiply, divided. They are laborious, meaning they take effort when you have to do 1 million of them. That's a lot of stuff. For example, the bank wants to know how much money. Well, you have to add all the bank accounts of all your clients. So, laborious, Pascal, one of the gods, okay, like Zeus, etc. Pascal is one of the gods of information technology. French merchant, inventor, punch board and card. This thing. This is a way to store data. On the CD, sul compact disc, c'è una roba. Ok? 0 più 0, delle fossette, no, fossette. Back then, they only had paper to store data, so they stored digital data on paper. You put a hole, that's 1. You don't put a hole, that's 0. Avete mai visto un carillon? È scritto in digitale, la canzone è in digitale, in binario. Per cui, se c'è il puntino, la nota musicale avviene. Se non c'è, no. Quindi on, c'è, non c'è. Girate. Sì, no, 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 sì, no, no. Same concept. This is a lot of data in binary. I will go through fast because we saw them last time, and so you can still look at them. Loose definition of computer device that store and processes data according to a set of instructions. Very nice. set of instructions. There is data, we can process it according to the instruction. CPU, memory, CPU is the processor, the control processing unit. The main memory, the bus where the data takes the bus, and you got a lot of software engineers. They take the bus. But wait, USB, the P is bus. Universal something bus. Universal system bus. The first model in the electronic digital computer was called this, or ABC, 1942, at Iowa State University. Binary digit calculation using bistable vacuum tubes. Organize the system in which computation and memory are separated. The vacuum tube trial. The first one. It's a moth, una falena. In the relay computers, vacuum tube computers, anyway, computers that had mechanical moving parts and were big, one of the problems were literal bugs. Falene, ragni. E questo è il primo bug della storia. C'era una falena nel posto sbagliato. Non funzionava meccanicamente la macchina. The game changer, the transistor. And this is the system. Maybe a tattoo, something. I don't have this time. Binary code, very simple. You saw it. You count 1, 10, 11, 100, 1, 110, 11, 1000, 110. Sorry if you're getting easy. So, the 1000, the hundreds, and the tens, and the ones, the decimal number, four, no, what's it? Decimal. Anyone help me? Can you guess why they're putting 1, 2, 3, 4 below 1010? Oh, okay, it's the example. So they want you to write down the 1234. You have the map, result. Okay. Yeah, very nice. Yeah, that's one. This is more simple. So this is 7 bits. You count them 1, 2, 3, 4, 5, 6, 7. 8. 8 bits. It has a name. What's the name of 8 bits? That would be simple. No, there is another name for 8 bits. Right. Now, watch out when you get a plan for your phone, the internet plan. They will tell you, oh, 100 bits. Well, get the bytes, the bit and the byte. So 11000000 is 192. Binary positional notation. Yeah, basically they're telling you that the mathematical way to read a binary number uses the power of 2. The same for decimal. 10 to the power of 0, 0, 10 to the power of 1, 10 to the power of 2, 100, 10 to the power of 3, and so on. Now, since this is binary, it's 2 to the power of 0 to the power of 1, base 2, 1. And again, they show you how they get 190. Would you like to have this in the example? Could I ask you put the pi and you give me the decimal? Yes, sir. Yeah. But it's a simple question, right? So you're not convinced. Come to the oh, I'm sure you would. Wait, I have to. No, you cannot come to because there's no drawing available. It's full screen. It's all stuff. Okay, but remember this 1, 2, 4, 8, 16. So let's go to yeah, this one is fine. So to obtain 192, we wrote 11000000. So this one represents 128, and this one represents 60. If it was decimal, this one represents 1. This one represents 10. This one would represent 100. That's exactly the same concept, but the one here represents 1. The one here represents 2. The one here represents 4. So how do we represent 33? Excuse me? Yes. 1 here and 1 here. 32 plus 1, 33. How about 11? Yes. 8 plus 3. 1, 0, 1, 1. And the rest here, 0. Easy? We put it in the exam? Hmm? So here, sorry. It can be done. Come on. You also have an excuse to meet up with the group. All of you have an excuse to meet up and study together, practice, binary. Hmm? Good. This is going to be in the exam. Not many, because it's not a computer science exam. It's just, do you understand binary? Probably not. Okay, for example, 11 plus before 8 plus 2 plus 1. The binary positional narrative is useful in converting dotted decimal or address file. Yes. We talked about this. The IP address. When you connect to the internet, you have an IP address. What's our IP address today? Can you please check? Again, slowly. Okay. 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 That's the IP address inside this room. When you see 192, it's a local IP address. Inside this room, we have this IP address. What's our IP address to the outside room? Who's gonna tell me? Do you know how to get the IP address that we have outside this room? The IP address of this router? No, it changes every time. Unless you have static IP, which they don't. Stefano doesn't have static. So it's new every time it's connected. 93.49.44.7. So those numbers are 4 bytes, meaning that they can only be between 0 and 255. 1 byte is maximum 255. When you put 1, 1, 1, 1, 1, 1, 1, 1, all 1, that's the highest number you can represent. And that's 255. 128 plus 64 plus 32 plus 16 plus 84 plus 1 is 255. So they thought, okay, let's use 4 bytes, and that's the IP address. I connect to the internet. My machine will send 4 bytes. In fact, the host will send 4 bytes to the client, telling me you are this client. You are 94.144. And how many combinations are there? What was it? 3 billion? Yeah, that's not enough. 3 billion combinations is not enough. IPv6, which is what advanced countries are using, have a lot more combinations. I don't know who's. This is the next slide. More than the grains of sand of all the planets, all the galaxies, a certain percent of the planet. Hexadecimal. That's another interest. Instead of base 2 is base 16. Wait, fixed base 16. Very useful for physics. And since there is no number greater than 9, they use A, B, C, D, E, F. They could have used anything else. I don't know, like plus, heart, smiley face, doesn't matter. They needed 16 symbols. We already have 10 symbols from 0 to 9. These are the other 6. So what comes after F? Minus F? No. But it's not 10, 17. You go to the next digit and put it on the left. So 10 in hexadecimal is 17. Imagine there is only until 9. What's the next one? 10. Meaning actually 10. But you have F, but it doesn't matter. It's 10. Then what comes? 11, 12, 13, 14, 15, 16, 17, 18, 19. 1A. Our language doesn't have that number, but 1A. 1B, 1C, 1D, 1E, 1F. Okay, convert decimal 168 to binary. It's similar. I'm not going to put this in the exam. Okay, hexadecimal 185, 5F, C. Characters. So, all the characters on the keyboard, they encoded them so that the keyboard doesn't send much data. When you punch a key on the keyboard, something is sent to the computer. They decided to use, okay, it doesn't have it, this table, but it's the byte. They encoded the entire keyboard with one byte, meaning that there are maximum 255 different keys on the keyboard. So hexadecimal and this table is missing binary. For the ASCII code. There is of course a problem. If you are in Indonesia, characters are different. If you are in China, there are more than 26 letters, 10 numbers, capital letter, accents. They go way beyond, so they use other methods. But since computers mostly speak English, ASCII is fine, 255 characters, still the standard. And that's pretty much what you want to fit on a keyboard. You don't want more than that. In fact, they are less. The keyboards, they have 120, 130, depending if there's a keypad or not. Okay, Mac. When you buy an object, technology object, there is an address called Mac. Big address. And it's a way to identify one single machine. So your IP address was your address in a network. The MAC address is actually the name of your machine, of your device. And hexadecimal. 1, 2, 3, 4, 5, 6 positions in hexadecimal. Find the MAC address of your phone. It's somewhere in device information or something like that. This device or search inside of I will check mine. I have Android. Okay, it gives me the MAC address of my Bluetooth device inside the phone. Do you have it? Okay, can you read it out loud and slowly? Okay, so he just read 6 numbers in hexadecimal. And inside the phone, there is more than one object, more than one device. The Wi-Fi alone is a device. Your Bluetooth module is a device. It has an address. How many MAC addresses are possible? How do we calculate? You should have done a bit of combinatoric in high school. How many possible outcomes do I have if I roll two dice? To tiro due dadi. Sono possibili combinare. If you're curious, go see that. It's a very nice theory. Grazie mille, Luca. To YouTube, the Earth is near. No, home. Do it at home, and it's a nice theory. Okay, I'm not telling you this as a professor that tells you this is how. It's a nice theory. Go see it. Physics has been changing a lot recently. The age of the universe, now that James Webb Telescope is observing the distant universe, they had to change the age of the universe. It's not 13 billion years anymore. It's at least double. So that's quite a big change for a known science such as the age of the universe. Okay, let's go to the next set of slides. Oh no, we were looking at the Cambrian, yes, okay. Machine calculations started early in human history. That's another key point of this PDF. Pascal, year 1600. Also, remember that many things, many concepts about computers were created before computers. They knew computers would come, so they just did it before the computer. Turing and von Neumann conceptualized the modern computer as a machine that processes data according to a set of instructions. So the idea that a program is a set of instructions. Now, it's a given that it's a set of instructions, but then it was not a given. In fact, nothing back then was a set of instructions. L'abaco non era un set di istruzioni, poteva fare solo una istruzione, sommare. Quindi il concetto di che sia un set, uno dopo l'altro, è nuovo. Computer data are in binary format, familiarizing with binary and hexadecimal notations, blah, blah, subjects where this format are heavily used. Early computer were large, expensive, used a lot of power, and were very limited in storage and processing power. Now, if you read this sentence, it's the same in 2023. They are large. If you want a supercomputer today, it is large. It's an entire room. Amazon Web Services, it's entire cities of warehouses if you put all the warehouses together. Expensive? Yeah, sure. You buy an expensive computer, it's expensive. They use a lot of power, yes. In fact, many warehouses of computers are in cold places, like Iceland. Iceland is starting to have a lot of computer farms because it's cold, so all the energy, all the heat of the computers is cooled down by the cold weather. They're limited in storage. Yes, we can never have enough storage. I recently reached the limit of my phone, so I have to start erasing or transferring to a bigger storage in my house. And the processing power, yes. There is always going to be a game that you can't play because you don't have enough processing. It was 51. Was it 51 pages? No, come on. Oh, cool. It was. Okay, the transistor, the central processing unit. Just as a curiosity, okay, I'm not going to put this in the exams, too much in depth. But yeah, control unit, arithmetic, memory, external storage, output devices, input devices. Basically, it's all a consequence of the logic gates. They are blocks, they are connected. Some of them do math, some of them do internet connection, and so on. So the unit control, arithmetic, logic, memory, external storage. It's self-explanatory. Plus, the way computers are built, at least until today, they reflect the way that the brain works. Have you ever thought about it? For example, there is the long-term storage that's slow. Then there is the RAM, the memory, which is fast. And it's like stuff that, for example, I'm making a cake. I read the recipe. That recipe goes in the RAM. The storage that I'm using now, the fast access memory. If you ask me the recipe of the cake 5 years later, it will take me a moment. Was it 200 grams? Oh, yeah. Yeah, then there was the butter. Slow. I'm accessing my hard drive, the long-term storage. But if I'm making the cake, you ask me how many grams of sugar? 200. Then there is a part that is good at math. In fact, you can train your brain. You do exercises. You guys are all doing something else. I'm over here. If you train your brain to do math, you will exercise math with an application. You will improve math. So you will improve that part of the brain that does math. Drawing, same thing. So just like the processor, there are parts that are specific to some tasks. And there are tools, the brush, the gun, the calculator and graph and pen, whatever tools you're using. They're like the applications, and you get results. And there is an input and there is an output. We communicate. There are languages. I teach him to do something, I give him a set of instructions. The recipe of a cake, it's a set of instructions. How to build a cake. And the more you look into it, into details, for both the computer and the brain, the more you will find similarity. Now with AI, it's even more close, the way it behaves. Okay, the bus. In computer architecture, a bus is a communication system that transfers data between components. If there is data, it has to move, it will take the bus. Punch card, magnetic tape. Yeah, how far back do you remember? Now the storage is flash memories and SD cards. What was before that? Okay, but before that? No, hard disk is still there, still there. The portable one, you know, hard disk is not portable. What was the portable storage before the pen drive? No, there was the CD. Okay, before the CD, the floppy disk, there was stuff in between, but the floppy disk. And what before that? What was before the floppy disk? Have you ever heard of the Amiga, Commodore 64? Yeah. Commodore is before Nintendo, before PlayStation, before all of that. The memory where the data was written was a tape. You know the music cassette? That's where the memory was stored. And it literally was an audio tape saying 10011, not with the voice, but the signal was an audio signal. And in the audio was 010. And if you wanted to run a different program, you had the playlist. Minute 215 is this program. So you had to rewind. Minute 215, play, turn on the computer, which wasn't a computer, but computer, and the program started. I have it, the Commodore. So, punch card, magnetic tape is the cassette. Punch cards, yeah. And the vinyl also had a bit of history in this. There was also at some point a string with ink in very, very early times. Someone invented a method to send images through the telephone wire, but it wasn't really digital. And the drawing was basically on a string with ink, and the string would roll. Crazy stuff. Go look it up. Okay, before the microprocessor. Before microprocessors, computers were built using rack of circuit boards with integrated circuit. Most companies, including Texas Instruments, were trying to integrate the functions of a CPU in a single chip. Same stuff today. They try to make everything more together so that a lot of functions are in the same thing. My computer at home has AMD processor. The graphics card is in the processor. There are also Intel with processors with the graphics card, the internal graphics card. Just put it. Then they are trying now to put in the 5G chip in the processor of the phones, so it's all together. Story of humankind. You know that these things usually go together. You put them in a package. The invention of the microprocessor. Intel had a contract from Busicom, a Japanese manufacturer. So in 1971, Fagin led the team that developed the 4004. That is an entire computer on a single chip, the microprocessor. Microprocessor revolution. Here you can see the 404, the upright. Those are the contacts. On, they can be on and off. Okay. So, for example, you can use it for your garden. The code inside says every 2 hours, this pin goes on for 10 minutes. And you put this pin in the sprinkler system, the watering system of the garden. This signal goes to the pump. So every 2 hours, the pump will be on for 20 minutes. And so on. Until we have our process. Nice one, they have very few pins. These are pins. Now these, the big ones, they have more than 1,000. You look at the pins, more than 1,000. In your washing machine, you have simple stuff. It's more like, because the washing machines of today have 10 different LEDs, 25 different programs, the valve for the softener, the soap, the motor can have different speeds, there is a beeping sound. So every one of these can be a signal to an LED, a motor, or it can be a button that you press, it turns on. So you tell this pin on. Okay, this is old. They have more pins now. The Intel processors and programming a CPU. A program sequence of stored instructions. I don't want to put this much. Okay. These are the two big brands nowadays for personal computing. They're not the only ones. In fact, they're not even the ones that make the most money. There are more alarm clocks than laptops, for example, or more televisions than laptops. The TV doesn't have only a processor, which is not used to anyway. For example, there is a small processing unit to charge batteries. So there are more of those. There are more batteries in your life than there are phones or tablets. You're charging the smoke thing, for example, the IQOS, and any other thing you know, the torch, other things. But for personal computers, AMD, Intel, they're the two big players. The only two. You're not going to have a personal PC with something. They have internet. Is it? Can you check? They used to, but I think they have Intel or Intel compatible, meaning that they're building from a license of Intel. Okay, can you check? Yes. Who builds M3 Go processor? Who built it? Apple. Okay, we have to go more into depth because, for example, the iPhone is not built by Apple, built by a factory in China. So, no. Apple, who built it? Does Intel build M3 Apple processor? Although people who makes the M3 chip, so starting in 2020, apparently they now produce the whatever that is, but if you are designing black rectangles and one day you wake up and there's less papers using photons and gray silicon, no. So, in a way, it's somehow also because that's the same. Okay, then there is this is the stuff you find in the washing machine. They don't do high level logic like matrix vector calculation. They do normal instructions. When the temperature is high, then stop the pump. When this, that, on your bicycle, stuff like that. Arduino, ever heard of Arduino? Huh? Yeah, it's ARM based. Arduino is ARM based. It can control LEDs, temperature sensors, small servos, stuff like that. Okay, multi-core. This is the die of a multi-core processor. These are basically the same. They work in parallel. As we said, we cannot make this smaller, or we cannot pack more stuff in it. So they have to be more. They work in parallel to speed up. Two of them can work hypothetically twice the time. Key points. With transistor and arithmetic and logic function, wire logic, programming, logic, computer logic. Just take to the fact that it's transistor. We don't have any other two. It's only switches on. Okay. There is something else in storages when you store zeros and ones, whether it's a hard drive, a pen drive, magnetic tape. Now they have the solid state hard drive. Anyone has solid state SSD hard drive? You have it? The best ones are NAND based, and now you know that NAND is not N. So the building block is a NAND, but there are also tiny capacitors. There's other stuff. But the processor is it's a whole bunch. No, come on. Who said well, you? It's a switch. Read, say, you can skip that. Okay, you said some processors are specific. So GPU is for graphics, graphic processor unit. It's specialized in 3D objects, vectors, reflections, those types of calculations. Finite element analysis, when you crash a car in a game, they're doing finite element analysis on the car that crashed. So that's specific of the graphics. AI, there are processors that are specific for AI. Blockchain accelerator, when you have to solve the cryptocurrency blockchain, you have to solve cryptography stuff. You can make specific sets of transistors that calculate just that. To calculate the SHA-256, instead of using adders, instead of adding 100 times with an adder, they put all the transistors in a way that the hardware will do the calculation one step. Okay? So I write hello in the input bits. The output bits have SHA-256. One set of transistors that does that. Okay, good. Next slide. Video. Again, we're going fast because these things, they are not what the course is about. We look at them, they're interesting, and they create the basis, but it's not what the course is about. Management information system, number 4. I will send you all these tonight. Wait, transistor, that's what we just did, yes. Yeah, back. Number 5. Okay, so a program we said is a set of instructions. Programs are written in high-level languages. The lowest level is the transistors. The highest level is English. When you write a program, you're basically using English. If A plus B greater than 5, then open file this and this. It's literally that. It's written in English, basically. That's the high-level program. Something will take the high-level programming, compile it into binary for the machine. For execution, they are translated in machine language by interpreter, executed line by line, the compiler, and then executed. So, some languages we have as humans, we have English, Italian, Spanish. Computers have Fortran, COBOL, BASIC, C++, Python, Java. The name Python comes from the Monty Python, the actors, comedy actors. They're from the previous century. There you go. A program in C++. Include IO string, which is to find the IO string stuff where so it's including the line string. Using namespace std main is the main program. We're gonna use two numbers in the program, and they are big. Float is a big sum. Could have been byte, so I know the number is between 0 and 255, but it's a float. So it's between 0 and 255. See out, it means to the screen on the monitor, like this. Inserisce il primo numero. See in, it's waiting for the keyboard. No, but you don't need to memorize. Just think it as a something. So see in, it's coming from the keyboard. I'm writing number 1. See out, inserisci il secondo numero. See in, I put the second. If n1 larger than n2, then see out on the screen. Il primo è maggiore del secondo. Else, so if not this, it's something else like this. See out, il primo non è maggiore. Okay? Show me one. Random there is something important. For I equals 1, I1 and 1 each time. J equals to the state, is equals to J over 5. Yeah, un set di numeri. Okay, so you can see this I read that thing. It was not in German, not in French. It was in C, language C, or C++. So people that make programs, they literally talk. I would like to. It has across so the program. AI is a lot of it's conditions, it's situation. You're taking this. Yes, those are operations on strings. Compilation success. It was turned from text to binary. And this is how the program looks. Inserisce il primo numero, the type 3, then the program tells me inserisce il secondo numero, that's 5. And then the program tells me il primo non è maggiore del secondo. Trust me, take a trip into coding, do it. There is no professor, no nothing. Just take it as something personal. Click this link and a C++ compilator try to modify the code, for example, 30%. What is the link? All right. cpp.sh. You will have the PDF going to or any other trip you want to take, online coding course. You don't need any software. A website will open and tell you, oh, now try to add two numbers. Now try to. Okay, numbers you enter that people. There is another condition. Earlier we had greater and smaller. So it could only be this is greater than this, or this is not greater. Or if it's the third condition. So they added this third condition. If n1 is identical to n2, then this. Okay. Okay, numbers yet. This is one of the possible solutions. Basically, this is the first language I learned. I was in first elementary. My mom was me the basic calculator was called. She didn't even know what she meant. It was amazing. It's a family of general purpose, high-level programming languages designed for ease of use. It really is very simple to learn. It's very English-oriented and also line-oriented instead of object-oriented. So the lines have numbers, the lines of. So you can tell the code, okay, if this happens, go to line 50. Goes to line 50 and there is numbers. You don't do the it's an object. There is no number often. Okay, we'll be able to balance and model the basic rules on the personal computer PC and then outlier. Dynamics of disruption. Technology improves, becomes competitive, mainstream. With time disruption, move upward disruption eventually at the SSO and customers, high-end customers. You do it in other courses. At some point, it becomes worth it to progress, to move forward in a field. For example, the field of cards, nothing forward since 1902, even before that, the first card. Pistols with fuel, 1 cent. Now, last years. Same with the computers. At some point, there is a demand for something, and that something will evolve. The Apple computer. Steve Jobs and Steve was here in a garage in Los Altos, California, built the first test computer that first pre-assembled computer. He was the marketing genius, Steve Jobs, and he was more of the tech genius. He invented the mouse. Was IBM personal computer. What was the brand of computers? First of all, anyone know? That's all 46. It was our idea. Big Blue was the kind of mainframe computer. They just showed that the completed computer would be assembled, shipped, installed, turnkey. IBM couldn't wait and see. IBM announced the PC IBM off-the-shelf parts. IBM PC needed an operating system. So at some point, they realized that every person on earth would own a computer. Now, go back to the video we saw, the university with 15 tons of relays. At some point, every person on the planet would own one. Not every university has one. Not every class has one. Not every student has one. Every single person on it has one. Way more. Imagine most of the devices you have in the folder. I have files, but I'm sure some of you will get two or three. Right? Do you have anyone has 2 laptops in the folder? Options are 2, 3. Yes. Now we got about right. So let's say every person. The Western world. But we may come. How many computers are sold? How many PCs are sold every year? I guess 800. Yeah. 1 million. Yeah, so every 80 years. No, every year 1 billion, which means 186 million. Okay, I expected. How about the phones? How many phones? $1.5 billion of phones. Okay. How about laptops? How many laptops? 116 million. Okay, so somebody is saying they are the same